All right, folks, we're back to this, and we would like to mathematically describe what's going on with interference here. So let's say that this point happens to be sitting at a distance y above the axis. This distance is d here, okay, and the angular position of the point is, well, call it theta. So this is sitting at an angle theta above the axis. I'd like to somehow, given that this distance is d, that this is theta, I'd like to see if this is going to be constructive or destructive interference. What it boils down to is delta x. The idea of delta x, the path difference, is key for interference. If there is a multiple of lambda, we got constructive interference. If it's an odd multiple of lambda over 2, we got destructive interference, and somewhere in between. We'll talk about the in-between later, as I mentioned last video. But for now, let's see if we can come up with an expression for this delta x in terms of the angular position of that point as measured from the x-axis. There are different ways you can do this, but typically what you do is you drop down a perpendicular, okay, from S1 to the line joining the two, to the line joining the center of the double slit to the point of interference, call it P. Okay? Don't get mixed up with P1, P2. P1 is path 1, P2 is path 2, and P is the point P. Right? So what you do is you drop down a perpendicular here, and because of small angles, what's interesting now is that this will be perpendicular here. Now, the slit, we're talking about what? Micrometers. Slit width is measured in micrometers usually. And we're going to play games here, and you're going to have to play games later on. If you don't do this method, do another method. It's not the only method to do this. You're going to have to play the same game in a different way. Do an approximation where something is small, and you have to figure a way around that. But for now, what we're going to do is drop a perpendicular down here, and because of small angles, we're going to call it perpendicular here too. The path difference now, which is key, this is what we're looking for. Remember, we're looking for the path difference between the two waves by the time they get to that point, and that path difference is, well, right here, right? This guy is, the path difference is in black right here. Why? Because, well, this is perpendicular down there. This is an isosceles triangle now, okay? This is perpendicular here. We'll call it perpendicular later. Don't have to do that right now. But you drop the perpendicular down to here. That's an isosceles triangle. The path from here to there is the same as the path from here to there, okay? So, am I in the way? So this path is the same as this path. So the paths are equal from here on, okay? And the path difference, which is key for, is this distance here. That is your path difference. And that guy will become critical for other discussions later. That path difference is, this is delta x. And what is it equal to? Well, look in this diagram. Remember the Mansour rule, right? You have, okay, what do we have here? That line is perpendicular to that line, and, well, that line is perpendicular to this line. So these two are perpendicular to these two, and if this is angle theta, then this is angle theta as well, okay? And this is d here, so this becomes, if this is 90 degrees, more or less, this guy, think about what this expression is, okay? Pause for a second, stop the video, and look at this. Double check that you are okay with this being perpendicular to that. That's how we drew it. That is perpendicular to this. That's how we drew it. Well, that's, this is horizontal, that's vertical. Theta, theta, same angle theta. So we'd like to, now we understand that from here on and from here on, the path is the same, and our key is always what? The path difference is what we want to find, and it's that distance here. What is that going to be equal to? Look in this triangle. Again, if this is 90, this is more or less 90 because of small angles, and if we're accepting that, if we accept that this is the case, which is okay to assume, if we accept that this is the case, right, then this distance, delta x, is equal to d sine theta. Okay, that's the path difference, and it depends on theta. The bigger theta is, the bigger this will be. When that is equal to m lambda, barring other sources of phase difference between the two waves, when that is equal to m lambda, we get constructive interference. And when that is equal to m plus a half lambda, we get destructive interference, and this is the key. So now the question is, are you able to predict the angular position of the mth maximum or nth minimum? Okay, what does that mean? Let's say I want to find what is the theta sub m. What does that mean? Okay, theta sub m is the angular position of the angular position of mth something. Angular position of mth. What does mth mean? 7th, 6th, whatever. M starts at what? M starts at, keep in mind, we have this formula there. M starts at 0. 0, 1, 2, 3. 0 allows us to, at m equals 0, we have the first destructive interference. M equals 0. What is m equals 0 on the screen? M equals 0 is here. Right? So what is theta? What angle corresponds to the position of the mth maximum? So again, m starts at 0. M equals 0, 1, 2, 3, so on and so forth. So theta m is the angular position of the m's. Let's say, I know, maximum. We're looking for the maximum or minimum, either or. What is that theta sub m? What is it equal to? Well, let's go here. And we say here, well, that's theta sub m. Well, what am I going to do? Say d sine theta sub m, which corresponds to the mth, whatever, maximum, minimum. If I'm looking for maxima, okay, this is equal to m lambda, and therefore sine theta sub m is equal to m lambda over d. So we're looking for the, let's say, sine theta 7 is equal to 7 lambda over d. And now we can put numbers on this. What is lambda? Lambda is visible light, like, you know, laser, like, I know, 500 nanometers, whatever. And d is the separation. So you can get an idea now, okay? You can do an order of magnitude calculation, whereby do that, please, on your own. If lambda is equal to, say, 500 nanometers, right? And d is equal to, I don't know, 12 micrometers. Where do you expect to see the 7th maximum on the screen? So 1, 2, 3, 4, 5, 6, 7, where will it be on the screen, right? So we have a vehicle now of predicting the angular positions of the, so this gives me the 7th maximum. 7th or mth maximum, you know, 7th maximum. And if I wanted the sine theta 7 for minima, okay, so this is for maxima, okay, would be, well, 7 plus a half, 7 plus a half lambda over d. And that's the 7th minimum. Okay? In this regard, we're calling the m equals 0, the zeroth maximum or zeroth minimum. Okay? Because we begin at m equals 0. All right, folks, so now we have a vehicle of predicting what the angular position of a given maximum or minimum is going to be, and all it depends upon is what order of interference are you looking at, what the wavelength is, which is 500 nanometers or whatever, and d, let's say 10 micrometers. Do a quick calculation and see, you know, what that angle is going to be. Pretty small, right? The reason you see these fringes is because the distance here is so big that eventually it results in a separation on the screen between maxima and minima. We're going to take a quick pause and continue shortly with playing more games with the double slit apparatus.